Okay, so welcome to our first online class. There's a few things that you need to know. We want to talk a little bit about remote learning. This document is found on Canvas in that first topic, that first section of introduction. And so I'm just going to go over it very quickly to talk about some things that you need to know before we get started. First off, you did really good about logging in with your name, so I can recognize who is who. So make sure you change your name to the name that we know by the school. Make sure that you test and make sure your camera and your mic is working before you log in, and make sure you get logged in the waiting room before class time begins. So you will not be counted tardy, because it's very important that you're in class when class begins. Sometimes you might be in the waiting room for a little bit of time because I do have to take attendance before I admit you in, so that is a process that takes a little bit of time. Make sure you have your cameras turned on and you're muted when you enter the classroom, and you can unmute yourself anytime that you want to ask questions, or you can also use the raise the hand feature. Raise your hand, but sometimes, especially when I'm writing on the kind of the notebook, I might not see your hand raise. So sometimes when I'm doing that writing and working out problems, I can't see everybody's picture. I can only see some of you. And so I might miss the hand raise. So if you still have a question and you notice that I'm not addressing it, just unmute yourself and ask me a question. And that's fine. So I'm pretty lenient about that. Make sure you kind of clean up your background a little bit. You don't want to be too distractive with things going on, like people passing or things happening in the background that could distract other people from learning calculus. I realize that sometimes online learning is much more challenging than learning in class, because you do have distractions. You have things that can happen that you have no control over in your house. You have other people there that are doing other things, and so I can understand that distraction. That's one thing for the muting of the mic, and just you have to be more disciplined and be focused so that you can still be an active learner, participate in the class. I expect you to be taking notes, especially actively participating in the class as we go. In short, do everything that we do in person. You're just in your classroom, in your house, working on this. I will call on you. Sometimes I'll leave it open for anyone to answer. And some days I do have a list of everybody in the class, and sometimes I'll just go through and randomly pick people's names and ask you to respond. So make sure you're paying attention. If you should need to go to the restroom, that's fine. Just send me a little note that just send me a private chat that you need to go to the restroom. I mean, I'm not going to hold you hostage, but I do need to know about that. So when I call on you and there's no response, I know why there's no response. So we need to know about that information. I also will often ask for some nonverbal feedback, such as I'll ask, okay, when you're ready, give me a thumbs up. And so I'll be looking for people to give thumbs up so that I know that we're ready to move on to the next topic. Sometimes I'll ask you to type into the chat a message. You can either do it to everybody or privately, and just say, when you finish the section of problems we're working on, just type in ready to go on or finish. And so I'll know that you're ready to move on. So we have those different kind of nonverbal feedback that sometimes happens. Speaking of the chat box, make sure you use it thoughtfully. I want you to use it. I want you to do comments, but be respectful in your comments and make sure that your conversations apply to the class. So you're asking me questions or getting clarification on what we're talking about in the class. And last one, when we do formal assessments, focusing mainly on thinking about your semester exam that's coming up, your Zoom camera must be turned on for the entire class. So ones that don't have don't have cameras, I think everybody, let me check. Okay, I still have a few not having me some cameras, so I need those cameras up and going. But by the time we do semester exams, they need to be, you have to have the camera turned on. We have to have the camera. I have to watch you take the semester exam and the formal assessments. Your camera should be showing your face and your upper body. And for those formal exams, your hands throughout, your face, your upper body, and your hands throughout. But be careful in the hands. So sort of like this would be a good one, so I can see the hands and I can see my upper body and I see my face. But you can't read my paper. So you don't want to do it like this where it's too close that someone else could zoom in and actually read what you're writing. So I don't want to see that much. More like this. Well, let me get a little bit closer. Like this. So I can see who it is, see your hands, and see that you're working. All other secondary electronic devices, such as phones or another iPad or something like that, needs to be away from you, from your work area when you're taking those formal assessments, with the exception, of course, of your calculator. Private chats during the entire exam is blocked, so make sure that you shouldn't be able to do all that, but don't even try. And remember that the school honor code still applies on these exams, so you need to be doing your own work and doing your own assessments. So that's just a quick review of what my expectations are for this remote learning experience that we'll be doing. Are there any questions about that? All right, so use substitution is the method that we're going to learn today. We're going to learn 3 main techniques that you'll see, 3 situations that are the most common. These are not the only ways that you'll use substitution, but they are the very most common methods that you will see and things to look at. The first method we're going to look at is called pattern recognition. And basically, you're just going to notice a pattern in order to integrate, because as you know, we don't have a product rule of integration, so we can't integrate when we have 2 things multiply together. And to deal with that, we use substitution is one of those techniques that we use to deal with this. And the first pattern you're going to recognize is you're going to have some function inside another function. So this is what that f of g of x means. So we have a composite function, so function inside of another function. But not only do you have another function inside another function, that inside function, if you differentiate the inside function, that gives you the extra thing you're multiplying by. That gives you this, that's what that derivative of the inside function is. And so that's the pattern we're looking at. We have some function inside another function, and if you look at that inside function, that's my inside function. And you take the derivative of that gives you what you're multiplying by. So this is the derivative of inside function. And basically, what you do is you find the antiderivative of the outside function with respect with the variable as the inside function. And that's it. And that's going to be how you're going to work it out. Now, this looks a little complex when you see it like this pattern. As we work through it, it comes much easier. So I'm going to do an example next to make this make more sense. Okay, so here we have the integral of 2x times x squared plus 1 squared dx. And so first thing I notice, I do have an inside function because x squared plus 1 is inside the square operation. So that makes it my inside function. And so that's going to be my use substitution. And so to work with this, what I'm going to do is I'm going to say I'm going to let u equal that inside function, 2x plus 1. And so the next step I need to do is I need to find the derivative of u. So derivative of u with respect to x. Well, does anybody know what the derivative of x squared plus 1 is?
X.
2x, very good. So that gives us 2x. Now here's a new thing that we're going to write this du dx slightly different method. And so I have du divided by dx. Well, I can do an operation by multiplying each side by dx, and I could rewrite this as du is equal to 2x dx. It's the same thing. Now, there's a mathematical reason why this works out. If you're curious about that, I uploaded one of Teacher Watt's video about why you can do this. And it's very fascinating. And it talks about the Pythagorean theorem, your equation, and your slope of your tangent line. And so if you're interested, I highly suggest you watch that video on Canvas. But for now, I'm just going to tell you we can do this. And when I do this, I notice something cool that happens. If you look at it, here I have 2x dx. So the derivative of my inside function is 2x dx. Well, look, that's everything that's left over in my function. So it fits the pattern. I have my inside function, that's f of g of x. That x squared minus 1 is inside the x squared function, the square function. And then this in the green is my derivative of u. So that fits the pattern. Once you notice that pattern that applies, you can rewrite your integral, replacing the inside function with u. So that x squared plus 1 squared becomes u squared. Replacing this 2x dx with what we figured it to equal to, which is du. And so now I have an integral written in one variable, the u variable, and I can integrate. So it's just a regular integration problem now. So the integral of u squared is what?
U divided by 3 cubed.
There you go. U cubed divided by 3. I'm going to go ahead and write it as 1/3, but it's the same thing as what you said. U cubed divided by 3 plus
C.
C. Don't forget your plus C on indefinite integrals. So we have 1/3 u cubed plus C. And so your last step, of course, is to go back to the original variable. So I'd rewrite this as 1/3 x squared plus 1 quantity cubed plus C. And you have now integrated your first problem using u substitution. So again, it's the recognizing the pattern, seeing that you have that inside function and the derivative of that inside function in your problem. Okay. So let's try this one. What would our u be equal to? What's our inside function?
X cubed plus 1.
Excellent. X cubed plus 1. Okay, so I'm going to take the derivative of that, derivative of u. And so what's the derivative of x cubed plus 1?
3x squared.
Perfect. 3x squared dx. So notice I'm just going ahead. This is always, you're going to always write it in this form. So you'll get the habit of just rewriting du dx straight to this when you're doing these integrals. Okay, so I'm going to check and see if I have the pattern I need. So here's my inside, x cubed plus 1. And then I notice that du is equal to 3x squared dx. So I'm checking to see if I have that. There's the 3x squared and there's the dx. So I have my u substitution pattern that I can do. So I'm going to substitute in. So I'm going to replace this with u, and I know the square root is the same as the 1/2 power. And I'm going to replace the green part with du. And so this is the actual problem I'm going to integrate. So what is the integral of u to the 1/2?
2/3 times the cube root of u squared.
Very good. I'm going to write it as a fraction. But okay, 2/3 u to the 3/2 plus c. And one thing you'll know by this time in calculus, they assume that you know fraction powers are radicals, and so you no longer have to convert it to a radical if you do not want to, now that we've proved it. So even though the original problem's in radicals, you can leave this in a fraction power if you want. If you want to go to radicals, that's fine. You can do that. If you do it as a radical, of course, this would be the square root of x cubed plus 1 cubed plus c. So either answer is correct. if you want to do it that way. Okay, I want to pause and let you try this next one. It's a little bit challenging. Think about your derivatives of trig functions to try to figure out which is going to be your actual inside. This one might be a little confusing and which one should be the inside. So think about what's the derivative of secant and what's the derivative of tangent to help you figure out which one should be which. Okay, so this one's a little bit challenging. Let's see. What do you think your inside function is?
Tan x plus 3.
Excellent. Okay, because you want to use the tan x plus 3 as your inside function because of, we know what the derivative of tangent is. So what's the derivative of this tangent x plus 3?
Secant squared.
Excellent. It is secant squared x dx. Okay, and so I did that so I can notice now I have that secant squared dx that matches up with our derivative here. So sometimes you have to think about it because you might have thought, well, secant x is inside the square operation, and you might have wanted to do with that, but you had a problem if you chose secant as your inside function because the derivative of secant is secant tangent, and you're missing the secant over here, so you couldn't do that. So you have to kind of really think about what your derivatives are in order to figure out what needs to go in there. So I'm going to do my substitution in. So tangent x plus 3 is u. Secant squared x dx is du. And so I can integrate. What's the integral of u du?
1/2 u squared plus c.
Excellent. And so now I can go and substitute in u, which is tangent x plus 3 squared plus c. And you're done. So not so hard. You just have to recognize your inside function and make sure what's left over that you're multiplying that inside function by is the derivative of that inside function. Well, that does sound easy, but you know it always gets a little bit more challenging. There's always something else that happens. And there's two situations that occurs most often in this. The one is maybe what's left over that I'm multiplying the inside function by is it has the essential part of my derivative. That means it has the right variable, but it's missing some constant multiple. And that's this next technique that we're going to look at how to deal with that situation. So you're going to start these like we have been. What is our inside function for this integral?
X squared plus 1.
Excellent. I'm going to let u equal x squared plus 1. That's my inside. And what is the derivative of x squared plus 1?
Just x.
2. There you go. I see it. 2x dx. Because we have to bring that power to the front. And so here, that's the problem. Because over in our equation, we have only x dx. But here we have 2x dx. We have the right variable, but we're off by a multiple, by some constant, some number is wrong. It's really easy to fix. When it's off by just a constant like this, I'm going to solve this little equation here so that I get x dx, so I can substitute it in. So the thing that's wrong is I'm multiplying by 2. So to fix that, I'm going to divide everything by 2. And so now I get du divided by 2 is equal to x dx. And now what I have over here is equal to this part here. So I might need to rewrite this equation or a derivative equation so that I can substitute it into my original function. So that's the extra challenge, the extra step that happens when you're missing a constant multiple. And so now I can go over here. I can replace the yellow with my integral from u squared. And I can replace the green part, x dx, with du over 2. But I know du over 2 is the same as 1/2 du. And I also know that we have that rule about constant multiples. And so I can always factor out a constant from an integral. So I'm going to factor that 1/2 out. And that's going to leave me with u squared du. Now this looks like an integral I can actually integrate. And it looks like ones we've been doing. So now I'll be ready to integrate. And what is the integral of u squared du? No one sure? What's the integral of u squared du?
1/3 u cubed.
1/3 u cubed plus my c. So multiplying that gets me 1/6 u, which I know to be defined as x squared plus 1 cubed plus c. And that's it. So it's not that hard. You just have to maybe rewrite your derivative equation a little bit so it matches up to the missing pieces of your equation. So that's the technique. This is this different technique. So try this one and see if you can figure out the correct way to integrate this. Identify your inside function, differentiate that, fix it so it matches what's left over, substitute, and then integrate. All right, let's check and see how you did. What would be our inside function? What would we let u equal?
4x cubed minus 9.
Excellent, 4x cubed minus 9. And so what's the derivative of that?
12x squared dx.
All right, so I'm going to check my function. And I have, this is my inside, so that's taken care of. And then what's left over is 6x squared dx. So how can I fix this so that it's 6x squared dx?
We would divide by 2.
We'll divide by 2. So I get du over 2 is equal to 6x squared dx. And so now I got, and we can go ahead and do this in one step, that 1/2 du, I can bring out that 1/2. So I got 1/2, the integral, 1 over u cubed. So that's the same as u to the negative 3. And 6x squared dx is that du, because I've already taken out that 1/2. So that's the 1/2 du over 2. So this is where we get our integral. So I just need to figure out what the integral of u to the negative 3 is. What would that be?
Negative 1/2 u to the negative 2 power.
Perfect. Then our
Plus
plus
c.
c. So that's negative 1/4. And then u to the negative 2, that means that u needs to come down. So it's going to be u squared plus c. So negative 1 over 4x cubed minus, that looks like a plus sign, minus 9 squared plus c is your answer. Okay, so that's how we deal with it when it's just a number that is off. We're multiplying by a constant that is off. Our next technique that you might see, another common situation, is where the essential part is the variable. So the variable part of the derivative of the inside function is missing either a variable or it has an extra variable. So something's wrong. You're missing some key part. The variable part is messed up. So it's not just the number, it's the variable that is wrong. So you don't have the right variable to the right degree. And so you need to fix that. And in order to do that, we have to use a new process in this, which is called the change of variables. So I have to use a technique called the change of variables to fix this type of situation. So you start it just like all the other problems we're doing today. You identify your inside function and you make u that inside function. So what would be our inside function in this case?
2x minus 1.
Excellent. So it's going to be 2x minus 1. So what's the derivative of 2x minus 1? 2. I see that showing up on your faces. So derivative of 2x is 2. Derivative of negative 1 is 0. So it's just 2 dx. So I definitely have a problem here because I have x dx, but in the integral, there's no x. And I can't make an x. There's no x there. And so in order to fix that, what we're going to do is we're going to go back to this equation here where we said, okay, I know u is equal to 2x minus 1. So I'm going to replace this extra x that I can't do anything with in terms of u. So I need to replace this with something u. So I'm going to go to this equation here, and I'm going to solve for x. So I can substitute x in place of whatever this is in terms of u. So I'm going to rewrite this equation, getting x by itself. So I'm going to add 1 to each side, and then I'm going to divide by 2. So I know x is the same as u plus 1 divided by 2. So I'm going to replace this x here with that u plus 1 divided by 2. So I have u plus 1 divided by 2. And then I can replace my inside function, u squared minus 1, with u to the 1/2. Just rewriting that radical as a fraction power. But then I'm still stuck here. I got dx. So I'm going to do like we did before in that last method. I'm going to rewrite this so that dx is by itself. That means I need to divide by 2. And that gives me du over 2 is equal to dx. So I'm going to replace this dx with du over 2. Now, right now at this step, it looks kind of messy, but the key is everything is in terms of u. We've gotten rid of the x variable, and that's what we needed. That's our goal in this change of variable format, is we need to get rid of all the x variables, get everything turned into terms of u. First thing to clean this up is you want to factor out your constants. So I got a 1/2 and a 1/2 here. So I'm taking that out. That means I need to take out 1/4. So I have 1/4 taken out. That leaves me with u plus 1 times u to the 1/2 times du. So it's starting to look a little neater, but we still have another problem. I still have a product. And remember, we cannot integrate with a product. But I realize that this is not raised to any power. This product would be easily fixed by just doing my distributive property. So that's what I'm going to do next, is I'm going to take u times u to the 1/2. So that's u to the 3/2 plus u to 1/2 times 1, which is u to the 1/2 du, because I can't, du, because I can integrate a sum or difference. I just can't integrate products. And so now I've fixed it so it follows the rules, the properties of integration that I know, and so I can integrate this. We're going to do it step by step. What's the integral of u to the 3/2? No idea? All right, so our rule is to add 1 to our exponent. So 3/2 plus 1 gives us 5/2. And then we multiply by the reciprocal of that, so that becomes 2/5. Okay, what's the integral of u to the 1/2?
2/3 u to the 3/2.
Excellent. And our plus c. So I'm going to clean this up a little bit. 1/4 times 2/5 is 1/10 u to the 5/2. 1/4 times 2/3 is 1/6 u to the 3/2. And I recall that u was equal to 2x minus 1. So we're substituting in the u back to our original variable. And there we integrate it. So this process requires a little bit extra work. And I knew I needed to do it because up here, this right here, I had the x variable that did not cancel out with this derivative of our inside function. And that's when you had to do the substitution, change of variable. You had to go back to using that change of variable format. Okay, pause a little bit, try this one, and see if you can solve this with that change of variable method. So identify your inside function, differentiate the inside function, and then if you cannot replace everything, do the change of variable by rewriting the u to what's missing, what's extra that we need to fix, and then simplifying and integrating. Okay, are we good to try this? Thumbs up if you're ready for me to try it.
I'll be right back. I have to get my dog. She's whining.
Okay. All right. I see pretty good response there, so I'll go ahead. What is our inside function?
X squared plus 1.
Excellent. X squared plus
Sorry.
1. No problem. Okay, and what is the derivative of that?
Two x dx.
2x dx. All right, so I'm going to check and see what I got going on in my problem. So my inside function is taken care of here. And then I got 2x dx. Uh-oh. I don't have any, I have x cubed dx, so I don't have the 2. So I'm going to go ahead and fix that. So I'm going to divide this by 2. Gives me a du over 2 is equal to x dx. And I can work with that because I got x cubed here. So I could rewrite this as x squared and then cube root of x squared plus 1 and then x dx. So I can move one of those x's over here. And so now I do have the x dx and the x dx. I got my inside function. But I do have this leftover. So I have x squared left over. So I have this leftover piece here that I need to fix. And so how do I fix that x squared part? You go back to this original equation where you have u is equal to x squared plus 1. And you solve this for what I'm missing. So I want to get x squared on the side by itself this time. So I'm going to subtract 1. And that gives me x squared. So now I know x squared is equal to u minus 1. So I can go to my integral here, replace the x squared with what it's equal to, u minus 1. Replace this x squared plus 1 with what it's equal to, which is u. So I get u to the 1/2. And then replace the green part, x dx, with what it's equal to, which is du over 2. So it's just doing all this substitution. That's the reason why all this is all called substitution method. You do a lot of substitution with it. So I'm going to clean this up. So I'm going to factor out my constant of 1/2. And that leaves me with u minus 1 times u to the 1/2 du. Again, I have a product. I cannot integrate a product, so I needed to use my distributive property and distribute this to everything in the parentheses. So that's 1/2 the integral of u to the 3/2 minus u to the 1/2 du. And that, we already did one with those integrals, so I'm just going to go ahead. The integral of u to the 3/2 is, we got u to the 5/2 and multiply by 2/5. minus, this becomes u to the 3/2, so I need to multiply by 2/3. And then our constant. This simplifies down to 1/5, u to the 5/2, minus, this simplifies down to 1/3, u to the 3/2. And I know u is x squared plus 1. So my final answer is 1/5 x squared plus 1 to the 5/2 power minus 1/3 times x squared plus 1 to the 3/2 power plus c. And that's where those are the most complex types that we're going to see with these u substitutions. Now I want you to go to Canvas and do the substitution method assignment and quizzes and work problems 1 through 8. So we're going to work problems 1 through 8. So I'm going to pause for a little bit.
Can
Actually
you
do
go
that.
back to that last slide so I can finish getting the notes?
Absolutely. How's that?
That's good.
All right. Okay, even if you haven't finished, we're going to go ahead and pause and we're going to learn our last technique. All this involves is how to solve it if you have a definite integral. If you have an upper limit and lower limit, and we need to evaluate the area underneath that curve, so we actually need to evaluate our integral. And so this is what you do when you do u substitution with indefinite integrals. If you'll notice, the key here is you start with the integral from a to b of, we have an inside function of f of x dx, and you have that derivative of the inside function. So it's set up in that u substitution form. So we want to recognize that pattern. So we got to get that pattern. If you have that set up, when you integrate, you're going to do the integral. Now notice I'm going to change my lower limit. It's no longer going to be a. I'm going to change it to g of a. So I have to substitute a into my inside function and figure out that value, and that's now going to be my new lower limit. And then I'm going to do the same thing with my upper limit. I'm going to substitute in b into my inside function, and that's going to give me my new upper limit. So that's the only extra steps, is substituting in this a and b into our inside function to figure out our new upper and lower limit of integration. And then we're going to do f of u du, and we don't have to go back to x's. We're now in the u variable. So let's see what this actually looks like in an example. So we're going to find the integral from 0 to 1 of x squared plus 1 cubed. So the first thing I notice is I do have an inside function. That's going to be my x squared plus 1 is my inside function. So I'm going to let u equal x squared plus 1. So I need to find the derivative of u to see if I need to fix anything over here. And the derivative of x squared plus 1 is 2x dx. So yes, I do need to fix something. It looks like an extra 2 because I need x dx, not 2x dx. So I'm going to fix that by getting rid of the 2. So du over 2 is equal to x dx. So now I have that part. So I have my u part fixed. And so I have the integral, and I'm going to wait to put my upper and lower limits yet because I haven't figured out what those values are, because I've changed my variable to u, so I can't use these. This is what x is, so I can't use the 0 and 1. But I can go ahead and substitute in. I have my u cubed, and I can replace x dx with du over 2. And so now I need to figure out my limits of integration. How we do that is we just kind of make a little table over here. And we're going to do our x value, and then we're going to do our u value, which is x squared plus 1. So I'm going to take my upper limit, which is 1, and I'm just going to plug that into this equation. So 1 squared plus 1 gives me 2. So my upper limit is now 2. Then my lower limit in terms of x was 0, so I'm going to plug that into my u value. So that's 0 squared plus 1. That gives me 1. So my lower limit is now 1. Make sure you change your limits of integration. This is the #1 missed thing on the definite integrals. People forget to change this and they go back and they use the 0 and 1. That's in terms of x, not y, so make sure you make note of it. So I'm ready to integrate, so I can factor out my constant. And I'm left with u cubed du. And I know the antiderivative of u cubed is 1/4 u to the 4th. Evaluate it from 1 to 2. Again, I'm going to go ahead and clean this up and get my constants out. So that's 1/8. U to the 4th evaluated from 1 to 2. So that means I need to plug in 2 to the 4th. And then I need to plug in 1 to the 4th. All right, so it gives us 1/8. And I know 2 to the 4th is 16 minus 1. So that's 15 times 1/8. So that's 15/8. So again, remember on definite integrals, you're going to get a single answer as you're going to get a numerical result. And so that is how we do definite integrals. Next one, I'm going to do some with trig. We haven't done too much trig here, so I want to refresh our memory on trig. So I have the integral from pi over 3 to 2 pi of 3 cosine squared x sine x dx. What do you think my u is, my inside function? All right.
The cosine?
X.
So this one's pretty hard because you got to think about, okay, I know the derivative of cosine is sine, but the derivative of sine is also cosine. So I got to figure out which one would be the best. And in this case, because cosine is squared, I would make that, you can remember, we can rewrite this as if it's 3 cosine x squared sine x dx. So cosine would be our inside function because it's in the ones that's squared. So this one's a little challenging when you have sine and cosine because they're so closely related. So I would do cosine of x would be your inside. So what is the derivative of cosine of x?
Sine x?
Close. Off by,
Negative
Sine x.
yeah, negative sine of x dx. So I need to fix that. So I got to divide by negative. So negative du equals sine x dx. So now I have that fixed. So this is my extra part here that I have. Now I have that extra constant there. That's okay. We can remember we can always just factor constants out. So we don't have to worry about that. So 3 is going to come out. I'll actually take a -3 out. And that left us with u, which is our cosine, squared. And then the green, the sine x dx, is du, because I've already dealt with the negative. So now I need to talk about my limits of integration. So I make a table. U is cosine x. So for my upper limit, is 2 pi. So I need to figure out what the cosine of 2 pi is. So anybody remember from the unit circle, what's the cosine of 2 pi?
1.
1. Excellent. So that's my new upper limit. And then pi over 3. What is the cosine of pi over 3?
This is the square root of 3 over 2, right?
That's the sine of pi over 3, but the cosine of pi over 3.
Oh, then that's the... Oh, what's that? It's like square root of 2 over... No.
You know how I remember my unit circle? This point here, I'm just going to do the first quadrant. I know this point here, this is 1 unit. So this is 1 comma 0. And then here is 0 comma 1. I know my 30, 45, and 60 follow a pattern in here. If I'm starting with cosine as my x values is 0, well, if I start with 0, then I have 1, 2, 3, square root each, divide by 2. And so it has to be 1/2. And then you can start, and it goes in the other direction in the other way. 0, 1, 2, 3. So this is 1/2 square root of 2 over 2, square root of 3 over 2. So it would be 1/2 would be our answer. So our lower limit is 1/2. So now I'm going to just integrate. Well, that's 1/3 u cubed. Evaluate it from 1/2 to 1. So that's negative 1 cubed minus 1/2 cubed. 1 minus 1/8. Well, that's going to be 7/8 times by negative 7/8 would be my answer. All right, last one before I let you work some more. What do you think our inside function is?
4 plus 2 sine of x.
Excellent. And derivative of u?
Is it 2 cosine x? Yeah.
Perfect. Yep. 2 cosine x dx. All right, so I'm going to check and see what's happening. What am I missing in my equation? I have the dx and I have the cosine of x. So I don't have that 2. So like we got to fix that. So I need to divide by 2. So du over 2 gives us that cosine x dx. All right, so I got the integral. 1/2 times the integral of u to the third in the denominator. So I'm going to bring that up and make that u to the negative 3. Replacing this with that du over 2, but I've already factored out that 1/2. And so now I need to deal with my limits of integration. So I make a table. This is the added step. U is 4 plus 2 sine of x. Upper limit was pi over 2. So 4 plus 2 sine of pi over 2. What is the sine of pi over 2?
That's also 1.
That's also 1. Yeah. So that gives us a 6. So my new upper limit is 6. 0 is my bottom here. So I got to do 4 plus 2. And what's the sine of 0 degrees? Or 0 radians?
0.
Yeah,
Starts at
0. So that gave us 4. And now we're ready to integrate. So that constant comes out. We add 1, so that becomes u to the negative 2. So we divide by the, multiply by the reciprocal, so that's negative 1/2. 4 to 6. Combine those fractions, so that's negative 1/4. And then u to the negative 2 is the same as 1 over u squared. So that's going to be 6 squared minus 1 over 4 squared. That's negative 1/4, 1 over 36 minus 1 over 16. All right. 1 over 36 minus 1 over 16. I'll cheat, and I've already figured this out. Negative 5 over 144. Times that by negative 1/4, that comes positive. 1 times 5 is 5. 4 times 144 is 576. So our answer is 5 divided by 576. Okay, questions over that. So the extra step is remember everything else we do at U substitution like we've learned earlier today. The extra step is this here where we have to change our limits of integration. key. Make note of that. Do not forget to change those limits of integration. I cannot tell you how often this is forgotten, and people will evaluate it with the X value, the original limits. So make note, make sure you always change that. Okay, so you can go back and continue working for the last few minutes of class. And I'm here to answer any questions. If you have any problems or if you get stuck or anything, ask me questions. You will have a video tonight on Ed Puzzle to do for our next class. Now, the video is by a teacher walk video, and it has to do with the derivatives of inverse trig functions. And I chose that because we're going to talk about the integrals of inverse trig functions, so you need to be familiar with the derivative first. And I think he does a wonderful job explaining how, using the Pythagorean theorem, how those values come about. And then at the very last of it, there's a nice list of all the formulas that you'll need to memorize to prepare for it. So make sure you look over that and start memorizing some of those derivatives, because we'll be needing that when we do integrals of inverse trig functions. All right, so I'll stop